2 minutes. Yep. All right, it's 12:30. Let's start it. Lord, thank you for bringing us together this afternoon. Thank you for all the things that you do for us. Everybody have a restful weekend. You help them to recharge, help them be ready to go. Help us stay focused and stay on target and just get everything done that we need to. In your name we pray. Amen. All right. I think I got all the things. Let's just make sure. There we go. Perfect. What are we doing today? Well, according to the slides that I inherited from my grandfather here, we will be recapping and right because I mean, depending on who you talk to, right, and the different rate my professor quotes and whatnot. Apparently, Dr. D is just learning the material as we go along anyway, so it's fine. So don't worry about it. I actually have had a student remark that Dr. D um, keeps saying that he doesn't know what's going on in class and that he's learning the material at the same time. So in case you guys know, when I say those things, that's a joke. Jokes are supposed to be funny. They are less funny when they have to be explained. Just throw that. Unless you're my son, and then you know, knock knock, who's there? Eyeballs. Right, that's the joke. That's a great joke. Everybody loves that joke. All right. Anyway, it's great. The first time it's great. The 500th time that you hear it. All right, matrices. Matrices. Indeed, matrices. I appreciate that it was spelled correctly and it wasn't matrices. Very, very nice. Very well done. Let's talk about matrices. Are people having issues creating the state space matrices? Because that's what I'm thinking is happening. So let's talk about it. I'm gonna have to add a slide here. I tried to do it on the whiteboard before, but nobody could read that. That's fine. Give me 1 sec. I'll add a couple slides and we will be good to go. Nope, no thank you. All right. So let's see. We'll come back to that in a second, even though there's not really anything else there. All right, so matrices, right? So when we're doing state space, what are we trying to get? We're trying to get two equations, really. We're trying to formulate these two vector matrix expressions. This is what we are trying to build, right? We want everything in this form. So how do we do it? Well, x, right, our state variable vector, x, depends on the order of our system, right? We will have as many x's as we have order of our system, right? So let's do an example here. Well, we'll get to the example. So what are we trying to do? Right? We know what x is. We define it, right? Typically, we pick energy storage variables, right? Because we want to make some prediction about what's going to happen to our system based off of how much energy there is in it and what the change in that energy is, right? So for example, mass on a spring, right? I pull it, I'm storing some energy via positional change, right? My input is storing up that energy, right? Because I'm changing how much energy is stored by pulling on it or pushing on it, right? Okay. Once I let go, that energy is going to be released, and all of that potential energy in the spring is going to be released as kinetic energy, which is why we pick position and velocity for many of our mechanical systems, because those are the two energy storage variables that we have. Okay, so with that being the case, right, let's do this for a very simple mechanical system, right? Second order mechanical system. Let's say that I've got this, right? Let's say this is our system, right? And I have to assign state variables. So I'm going to have x1 is equal to z and x2 is equal to z dot. And then if I just want to, if I want to make my x dot matrix, right, this is where it comes from, right? We just take the time derivative of x1 and x2. But what are we trying to do, right? We want to develop state variable equations, right? Because if I can get my state variable equations, I should be able to get my state space matrix for a linear system, okay? So what are the state variable equations? Well, I'm trying to create equations of this form where I have x dot n is equal to some function of a combination of my state variables and my inputs, right? The only thing that I want in this function for x dot are my state variables and my inputs. That's all that I want. Okay. All right, so for something like this, right, we automatically get a free equation, right, that x dot 1 is equal to x2. Where does that come from? Right here. Right? Z dot is equal to x dot 1, but it's also equal to x2. So x dot 1 equals x dot 2, right? Because it fulfills these requirements right here. So now I have an equation for x dot 1, right? And I know that z double dot is x dot 2 in this case, right? So I'm going to formulate my x dot 2 equation. How do I do that? I solve everything. I substitute in my state variables, and I solve everything for x dot, not double dot, sorry, x dot 2. And that's equal to what? Well, if I'm looking at this, right, this is going to be 1 over m times u plus, minus b over m times x2 minus k over m times x1. Okay, is everybody with me so far on how I got this, right? Because going from here to getting our matrices this is the step, right? If you have this, Dr. D claims that if I have this, I can set up my A matrix and my B matrix, right? That's what Dr. D said. But I didn't do myself any favors here, so I'm going to rewrite this. I'm going to rewrite both of these equations. I'll start with this one. Negative k over m x1 minus b over m x2 plus 1 over m times u. In this case, right, I think it's obvious, but I'll just write u is equal to u, right? Because I need something, need some input, right? Normally we have a force, u is equal to f of t or something. We're just gonna be simple here and say that we already know what u is, right? We know u. Okay. So look, I rewrote this in this way, right? I'm gonna rewrite the top one. Like this. Okay. I have it like this for a reason. For a reason. I want you to look at this right here. If I was to draw that like this, that looks like my x dot vector, right? So here's my x dot vector. That has to be equal to some matrix times x1, x2, right? Times my state vector plus some matrix times u. I only have one u, so it's just going to be u. Okay. I'm going to change colors here. I'm going to grab that and make this blue. Right, because I think that's pretty easy to see where the u's come from, right? 0, 1 over m. Where it gets tricky is with the x1 and x2 things, right? Because we need to understand what a linear combination is, right? When we talk about linear combinations in linear algebra, which I understand, we don't have much in terms of linear algebra, right? Maybe a little bit at the end of Calc 2, if things are to be believed. But the only thing left to us here is this portion, right? That's the only thing we haven't accounted for yet. I want you to look at this, right? 0 times x1 plus 1 times x2. Negative k over m minus b over m. The coefficients of these terms go in here. Why? Because remember, when we multiply matrices and vectors, it's row by column. So if I multiply this back out, I get 0 times x down. So, all right, I'm going to do another thing that's going to be really hard to see here because I only have a few colors. So bear with me. If I take that top row, right, that top equation, the x1 equation, right? The top row here should correspond to that. All right, so x dot 1 is equal to 0 times x1 plus 1 times x2 plus 0 times u, which is what we got, right? That's where we came from. The bottom row, the x dot 2 equation, x dot 2 is equal to negative k over m times x1 minus b over m times x2 plus 1 over m times u. Wait. Mm-hmm. So the way that we get x dot 1, right, is because, yeah, I mean, you get that the fact that z dot is equal to both x dot 1 and x2, right, is what we're going off of here, right? Because the relationship between velocity and position is what's driving part of this, right? Because if I change my position, I'm going to have a change in velocity, right? And that is accounted for in the x dot 1 equation. So how does the change in position of the spring affect the velocity of the system? Because it's going to. What do you mean? How do you use the equation for x dot 2 but not x dot 1? Yeah. Mhm. So is there a different way to get x dot one? Is that, oh no? No, right? The only way that we get x dot one in terms of our inputs and our outputs here is by the relationship between position and velocity for this particular system. That is the only way for this one. Think about it this way, right? In terms of potential and kinetic energy balance, right? If I start with the ball up here, it's got all of the potential energy, right? And none of the kinetic. I drop it, we are transferring our potential energy into our kinetic energy. By the time it hits the ground, it will have as much kinetic energy as it had potential energy at the top, assuming that there's no losses to heat or sound, which we know that there will be. So what I've just told you is absolute lie, right? But imagine if it were true though, that'd be awesome, right? But yeah, so in this, for this particular thing, right? Don't overthink it, right? The, the derivative of position is velocity. X dot one is equal to x2, right? The rest of it, right? If you can get to this, if you can get to these equations, right? And you order them like x1, x2, x3, all the way out to xn, right? You should be able to get to these matrices, right? Because you just look at the coefficients, you drop them in, right? So in the general case, right? In the general case, we'll talk about the Y matrix in a second, right? But let's talk about this general case here, right? In general, right? Right? We've got some n by n matrix filled with coefficients, right? And this is going to get multiplied by some vector that has n state variables, okay? So in the most general case, right, if we were given a state space representation, you could get back to your state variable equations, right? Because you would just have to, take this row times column, right? So if we do the first row here, right, we get A11, X1 plus A12, X2, all the way out to A1N, Xn, right? All we're doing is we're saying, because of the way that matrices and vectors behave, right? Because of the fact that it is a linear combination, it's not a straight multiplication, right? We can take the same equation, right, and run it in reverse and populate our matrices based off of what is in the coefficients of those variables in our equation, right? And so if you write them out in sequential order, you're actually doing yourself a favor because you should be able to just pop the coefficients into the appropriate slot. So right, this is not a linear algebra class, right? Right, and I realize I'm using big technical terms like pop this into that slot, right? And I know that's something that they would definitely say in a linear algebra class, 100%. Um, but beyond this, beyond being able to do this, right? There's not a lot that we need to know about linear algebra in this class. Okay, so understanding how to multiply vectors and matrices is the cornerstone of state space representation, right? It can only be done when we have a linear system. But if you can get to your state variable equations, right, then you should be able to hopefully see at least how I developed these matrices. Now, what about the output equation, right? Because that seems like really arbitrary. Well, it is, right? It all depends on what you want the output to be, right? Do you want it to be the velocity? Do you want it to be the position? What do you want? In the homework, you'll have noticed that, any state space representation problem tells you to measure specific variables, right? That's telling you what I want in the Y, right? Not because I don't trust that you guys would pick a valid y, right? But it's because I know you'll all pick valid y's, and then I'll have to grade a million different things. So I'm just trying to focus you guys onto specific outputs, right? So let's say for this case, we said, you know what? I'm going to have one output, and all I'm interested in here is the position z. That's it. I want to know what z is. Okay. Well, z is just x1. Because remember, look at this equation here, right? Look at this guy right here. This has the same format as the state equation, right? So I'm going to need everything in terms of x and u. This gives me y in terms of x and u. Now we know from doing examples last week on Thursday that we can have like x1 minus x3 as a valid output, right? We can have momentum if you believe the homework, right? You can do whatever linear operations you want to your output, right? And make it, if you wanted acceleration of the system, we could do that too, right? So let's keep it simple. Let's just keep it there, right? So if I want to make this equation, y1 is equal to x1, right? Well, what do I know? Well, y1, that's got to be equal to something times x1, x2, right? Because we know x plus some matrix times u. Remember, our equation that we're working with here is this. Or if we rewrite it, it's this. Well, that's all it is. So if it's helpful, do yourself a favor, rearrange your equations. I know some of them are long, right? And it's a long, arduous task. But for the price of another another minute of your time, it takes some of the guesswork out of it, right? And you can basically drop these coefficients in. That, yeah, Con. So, yes. Right, so this would be the output. Right, so whenever you ask for a complete state space, remember you need the x dot equation and you need the y equation, right? You need the state equation and you need the output equation.
I have a quick question.
Mm-hmm.
So if you wanted to get the velocity as an output, you just add a second row in for your C matrix, right? And then do it for X2.
Right, so if you wanted y2, right? Y2 is equal to x2, right?
Right.
So yeah. You just do that.
Oh, okay. I see. I think I was trying to pull it from my input equation in my head. Gotcha. So don't do that. Okay. Thank you.
Yep. In Simulink, if you're doing this in Simulink and you have multiple outputs, you're going to have to demux that before you send it to the scope. Just so you know. Okay. Any other questions? Is this a little bit help clarify? Maybe I should have done this a couple weeks ago when we talked about it. So our question is, if I just wanted velocity, right? So the top, if I just wanted velocity, right? Say y1 was equal to x2, right? Because remember x2 is z dot, right? All right, so let's talk about it, right? So if you're given only one, right? And in this case, we're saying, well, y1 is equal to x2, which is equal to z dot, right? I want the velocity of this mass, okay? Well, then y1 has to be equal to some matrix times my state vector plus some matrix times u. Well, we know that there's no u, right? We're basing everything off of this equation. Do I have anything times x1? No, that's going to be 0. The only thing I have is x2. And that would be it. If you were just asked for velocity, that's your output equation. Done. Right? A lot of the time, right, it seems trivial, kind of, right? Because you end up with a D matrix of 0 and, mostly zeros all over the place. And you're like, well, what's the point? Well, the point is that if you're doing it in Simulink or you're trying to do some analysis, right, all of these components are important because this is going to return us, the output that we want, right? This is how we're going to develop, right? How we develop our output response. Okay. Anything else? I mean, if you were to just look at this right now without any explanation, I would be really confused too. I don't know. There's a lot of lines and colors there. If you're colorblind, though, I guess it doesn't. I don't know what that has to do with anything. But you guys have any other questions? Yeah, Chris. I don't have my laptop here, so not today, unfortunately. We can talk more about it if you have time to come to office hours tomorrow. But yeah, if I had my laptop, yeah, we could talk about it. But unfortunately, the classroom computers do not have MATLAB in them. Seems like a gross oversight, but it's the world we live in. All right. Any other questions? No. Well, let's watch a video. This one is going to seem kind of long, but it's, at least I think it's interesting.
This video was sponsored by Brilliant. Here we have a mass on a spring. If I pull it back and release, one of 4 things is going to happen. First is completely sinusoidal motion, as in it will oscillate back and forth forever, which will happen if there's no air resistance or damping present. 2 is exponential decay. This happens if we put in some thick or viscous fluid, which will cause the mass to exponentially decay to equilibrium without overshooting. Yes, this entire video will assume damping force is a multiple of velocity. 3 is a combination of the first 2, which happens when the damping isn't as strong or the spring itself is stronger. In this case, the spring will oscillate but still decay in the process until it eventually settles. And 4, literally anything else can happen if we have some input force or just non-ideal conditions. We're not directly as concerned with this 4th case in this video, but we will have inputs later. The main emphasis though is these 3 functions, which is really 2, while the 3rd is just a combination. Now if I had to summarize what the Laplace transform visually tells us in just a few seconds, it'd be this. While the Fourier transform tells us which frequencies or sinusoids are present in a function, the Laplace transform tells us which sinusoids and exponentials are present in a function. In fact, we're soon going to see that the Fourier transform is just a slice of the Laplace transform. Now here's the Fourier transform equation. It takes in some function of time and outputs a function of omega that tells you which sinusoids are present in your signal. If you put in a pure cosine curve, then out comes a function with 1 spike, since your original curve was 1 sinusoid. Well, for real functions, these are symmetric about the y-axis, so you'll actually see 2 spikes. And the x-coordinates will match the angular frequency of the original signal. If you put in a non-periodic function, you'll get out something more complex, which tells us that it takes infinitely many sinusoids to make up this function on the right. This animation does a great job at showing the original function being a sum of all of those sinusoids, infinitely many, where the sum is seen in yellow, while the magnitude of the Fourier transform tells us relatively how strong each of those sinusoids is for any given frequency. One thing to note is that the y-intercept of the Fourier transform is the area under the curve of the original. Remember, this is the output when omega equals 0. And when omega equals 0, then this term goes to 1, and we have just the integral of the original function, aka the area under the curve. Now for a lot of this video, I'll be working with this equation or something similar, because it has a sinusoid and exponential component. However, we will assume it's 0 for all negative values of t, and it essentially turns on at time equals 0, which avoids the function diverging to infinity. So when we put it into the Fourier transform, out comes a complex function that I won't graph quite yet. I'm not worried about the calculus in this video, but if you just know integration by parts, you can do this, just treat I as a constant. Anyways, I'll FOIL the bottom here to get a new equation just with a separated real and imaginary component, and this is what we'll work with. This function only has one input, omega, so that can just go on a number line. But out of the function will come a complex number with a real and imaginary component. So we need two dimensions to represent that. So let's put in some values now. If omega equals 1, then the output becomes 1 over 1 plus 2i, but that can also be rewritten as 0.2 minus 0.4i, which will be plotted on the real and imaginary axis respectively for omega equals 1. Now this is a distance of roughly 0.45 from the origin, known as the magnitude, and that we can plot against the input at omega equals 1. This will be the magnitude of the Fourier transform. Now for omega equals 2 as the input, we get out 1 over negative 2 plus 4i, which simplifies to negative 0.1 minus 0.2i, and that will also go on the output graph. The magnitude for this is roughly 0.224, and that will also go on the magnitude plot for omega equals 2. And lastly, I'll plug in omega equals 0, which outputs just 0.5, no imaginary component, and that will also go on the magnitude plot. Remember, that 0.5 is just the area under the curve of our original function. Well, accounting for the fact that areas below the x-axis are negative. If I were to plot all the magnitudes for any input omega, we'd get this, the magnitude of the Fourier transform. Keep this plot in mind because it will show up soon, but now let's get to the Laplace transform so you can see just how similar it is to what we've done so far. So here we have the Fourier transform again, and this is the Laplace transform, nearly identical. This could also be negative infinity like above, by the way, but especially in engineering, we usually deal with signals that, like I said earlier, turn on at time equals 0, so we can analyze the transient response from there. The only other difference though is we have an s here instead of an I omega. But s is really alpha plus I omega, which I'll substitute in, because now we can separate that exponent into two terms. Now look at this. The Fourier transform of something is found by multiplying that function by e to the minus I omega t and integrating. Well, in the Laplace transform, we have the integral of something times e to the minus I omega t. Meaning the Laplace transform of some function is just the Fourier transform of that function times an exponential term. Doing this for all values of alpha, all real numbers, gives you the entire Laplace transform. To see what I mean by this, let's look at the Laplace transform of the same function as earlier, which again I'm not going to derive. But it's nearly identical to the Fourier transform. The only difference is s represents a complex number, which means the input will require two dimensions, one for the real and one for the imaginary component. The output, just like before, will be complex, so we need 4 dimensions for the Laplace transform in total. But notice that when alpha is 0, we get the exact same outputs as the Fourier transform. As in this alpha equals 0 line, or the imaginary axis of the Laplace transform, is the Fourier transform. Another way to see this is with the integral, because when alpha equals 0, the exponential goes to 1, and we're left with the original Fourier transform equation. So if I plug in something on that axis, we should get the same magnitudes as before. Like if we put in 0 for alpha and 0 for omega, which goes here on the input, then out comes 0.5, that area under the curve, which goes here on the output. And since I don't really have another dimension, I'll just write that magnitude above the corresponding input. If I plug in 1 for omega and 0 for alpha, which is also on the same axis, then out comes the 0.2 minus 0.4i from before, which on the output has a magnitude of roughly 0.45. And I won't show it, but if I did plug in this point where omega equals 2, the output would have a magnitude of about 0.224. If I was using a third dimension to plot those magnitudes, then we'd see the exact same function as before above that imaginary axis. We could also make a contour plot though. Like just imagine looking down on this graph where colors are assigned to different y values, because then those colors can represent the magnitudes. Then if I move the green line over to, let's say, alpha equals negative 0.5, the outputs will be the Fourier transform of something slightly different. Let me just put the original Laplace equation back up top, and you'll note that since there's already a negative sign here, when I plug in negative 0.5 for alpha, this will just calculate the Fourier transform of our original function times e to the positive 0.5t. That Fourier transform will look like this, and again, I could write the magnitudes to show the outputs, or I could use colors. If alpha is swept through the plane, we get the entire Laplace transform plot. And if we actually use a third dimension for those magnitudes, it would look like this. This plane here shown in green, which I'll fade the plot a little so you can see, is all the inputs s. X represents alpha, and y is really I omega. The 3D plot itself is the magnitude of the complex outputs. This is the Laplace transform of the original function e to the minus t sine of t. The thing is, this doesn't tell us much just by looking at it. So what I'm going to do is graph the equation alpha, or x, equals 0, that'll give us a plane as shown. Because remember, from before, the alpha equals 0 line actually yields the Fourier transform of the original function, which we can see with the intersecting curve. This is what I meant by the Fourier transform is a slice of the Laplace transform. But now I'm going to decrease alpha while also plotting the original function times e to the minus alpha t. Right now alpha is 0, so that exponential is just 1. But as I sweep alpha, we start to see both plots change. And what you're seeing with that intersection on the right is the Fourier transform of the plot on the left at any given time. Like here, I'll posit alpha equals negative 0.5 because this is what we just saw a minute ago, where the original curve times e to the positive 0.5t, because that double negative, has a Fourier transform with those two small peaks. Then I'll extend the range of z because as we get closer to alpha equals negative 1, we get an intersection with two much higher and narrower peaks where rendering also isn't looking so good. But anyways, this happens because the left plot is approaching just a regular sinusoid since the exponentials are about to cancel once we get to alpha equals negative 1. And we saw before that a pure sinusoid has a Fourier transform of two infinite spikes, which we can also see on the 3D plot. So the quick summary to what we've seen already is that to construct a Laplace transform, take whatever function you want to work with, multiply by e to the minus alpha t for some alpha, let's just change it to something random like negative 0.93, and graph the 2D Fourier transform of that function. Then keep doing that as you sweep through all values of alpha, stacking two-dimensional Fourier plots side by side until you get your 3D Laplace transform. You will likely not be shown this in a classroom setting, and that's because most of it pretty much doesn't matter. All we care about are these two peaks which do go to infinity, known as the poles. Now if we go back to the 2D plot, those poles are located at negative 1 plus and minus I, which we can represent with an x. Poles and also zeros, which doesn't apply to our function, are pretty much all you'll ever see for these plots. The reason the poles are there though is because if we plug in negative 1 plus or minus I into the Laplace equation, we get 1 over 0, which I'll just write as infinity, because on the plots those are represented with an x. And one more thing you'll notice, when I was sweeping the alpha plane, I stopped at those poles, or alpha equals negative 1, and never went behind that. That's because once alpha goes below negative 1, the function we were plotting diverges, which means the Fourier transform of this does as well. So the Laplace transform doesn't actually exist in that region, whereas this is the good region which we give a name to, the region of convergence. Just think of this region as all the alphas such that this part of the Laplace transform eventually converges to 0. This means everything I said earlier with taking the Fourier transform of this function and that being a slice of our plot is true, if that slice is in the region of convergence. This part is, so we're good there. However, this part is not, which is why, again, the function diverges for those alpha values. Essentially, this exponential term has now 1, making Laplace undefined in that region. Anyways, going back, notice that for our pole, the imaginary coordinate is 1 and -1, which matches the coefficient or angular frequency of our sinusoid. The real component of -1 matches the coefficient in the exponential term. This is finally what the Laplace transform visually tells us. The imaginary axis represents the sinusoids, and if my poles are on that axis, it means my original function is just sinusoidal, and the further from the origin the poles are, the higher frequency that signal is. If my poles are on the real axis, then there are only exponentials in the original signal, which decay faster as we move further from the origin. When the pole has real and imaginary components like here, then we have a combination. Since this graph is symmetric about the real axis, I'm going to move it down, and to help with visualizations, I'm going to change the x-axis so every tick mark is 0.2 units apart. But anyways, now the pole represents this function with that exponential and sinusoidal component whose graph looks like this. If I move the pole away from the x-axis, then the sinusoidal frequency increases, causing faster oscillations, and the resulting equation will have an angular frequency that matches what we see on the imaginary axis. If I move to the left, then the number in the exponent gets more negative, causing for a faster decay rate. The equation for this function still has coefficients that match what we see on the axes. And if I move to the right, then the decay rate slows until we reach the imaginary axis, where we get a pure sinusoid. And poles on the right-hand side correspond to functions with exponential growth. So now Laplace transform equations should make way more sense. Like sine of 3t has the Laplace transform of 3 over s squared plus 9. If we find the poles or when the denominator is 0, we get plus and minus 3i, and this tells us the original function has no exponential term, but it does have a sinusoid with an angular frequency of 3, which we already knew. However, the most common talking point you hear with Laplace is not anything we've seen so far, but rather its ability to turn calculus into algebra. If we take some arbitrary function x of t, it will have a corresponding Laplace transform x of s. But if you take the derivative of that same function, the Laplace transform will be the exact same thing times s. There is an extra term that has to do with initial conditions, but I will assume those are 0 from here on. Then the Laplace transform of the second derivative is again the same x of s times s squared this time. And some more initial condition terms that we'll ignore. This pattern would continue, and this is where Laplace is really useful. For example, this is the differential equation that describes a mass on a spring. We've got the force from the spring itself, the damping force, which is a multiple velocity, some arbitrary input x of t, and all forces summed to mass times acceleration here. The grouping of the terms just came from some rearranging. So what we can do is take the Laplace transform of both sides. However, due to linearity, this is the same as taking the Laplace transform of each individual term. The transform of some x of t is x of s, and for k times some y of t, it becomes k y of s. For by prime, from the rule above, we get out the same y of s times s, and the b is there as well. Then the second derivative outputs ms squared y of s. Since all the terms on the left have a y of s, I can factor that out to get this here. Some of you may know this part as the auxiliary or characteristic equation. We'll then isolate y of s and we're left with this here. So we may not know the actual output y of t, but like we've already seen, if I know when the denominator of the Laplace transform is 0, aka the poles, then I can tell you a lot about your output function. Let's assume the input is a constant force because this is the same as having a vertical spring where the mass is subject to gravity. Like good engineers will say the mass is 1, thus force is 10 newtons. And when the block is released at t equals 0, or the force is immediately turned on, so to speak, this is known as a step function written u of t, and its Laplace transform is 1 over s. Meaning our force, 10 u of t, becomes 10 over s, which we'll plug in for x of s. Then again, mass is 1, and let's say the damping coefficient is 0, while the spring constant is 1. Then I'll just move the s down to the denominator. Since there's no damping, the spring will oscillate forever around in equilibrium, but let's check that this is shown with our Laplace equation as well. We have one pole at positive I and another at negative I, which is what makes this part 0. Then we also have a pole at 0 from the s out here, and we'll put everything on the pole 0 plot. Again, I'm hiding the bottom to make room, but it always looks identical to the top half. And now we have everything we need. These poles say that the output will have a sinusoid with an angular frequency of 1, and we haven't seen a pole at the origin yet. But remember, this is the area under the curve, the intercept of the Fourier transform. The pole thus represents an infinite area, which just means there's some offset in our output, or something that doesn't converge to 0 to get that infinite area. Since we're considering the top to be y equals 0, then the output is exactly what we expected. If I increase the value of k or make the spring stronger, then the poles start to separate more and more, which represents faster oscillations about an equilibrium. If I were to add some damping now or increase b, then we expect slow exponential decay. I'll just stop here at b equals 2 for example, so we can see there's now a sinusoidal and exponential component to our equation, which matches what was expected, even though no, I'm not graphing the exact output. If we make the damping much stronger, we get to a point of critical damping, where finally oscillations go away and it's only exponential decay. Then moving from there, the exponential decay just slows down from this term not decaying as fast. Plotting the path those poles just took is the idea behind a root locus plot, by the way, for those in the controls class. But this is where the design part comes in, because by analyzing the locations of the poles, we can determine how a system will respond to different inputs. Many systems out there would be extremely difficult to solve using only functions of time. Plenty of you probably know how not fun this would be to solve using only differential equations. But moving to the S domain makes it an algebra problem that's much more doable. And especially in control systems, Laplace is crucial. I mean, we just did a problem where an input was multiplied by the system's transfer function and we got the output transform. It wasn't that bad. But even when there's more going on between the input and output, it simplifies fairly nicely when using the S domain, as we can still just multiply the input by a more complex but still manageable transfer function to find the corresponding output. Of course, there's plenty more to all this, and if you want to continue your learning, I highly recommend checking out Brilliant's series on differential equations.
No. No time for that. Anyway. So, a lot of stuff in there. Some of the stuff that we're going to go over today, like the properties of Laplace transforms and things like that. Yeah, I like this video. I think it helps to see the visualization of what a Laplace transform is actually doing, understanding how changing your parameters changes the dynamics of the system. Okay. Anyway, this is done. We're left with the lab, homework 5 and exam 2. All right, dates are good. So there's that. I bombarded you guys with announcements yesterday. Sorry, not sorry. Homework 4 solution, homework 5, parameters for the lab, the motor curve, Group 10 GCU announcements. There's a lot of stuff, so check it out if you haven't seen. Speaking of the lab, let's talk about the lab. What does the lab do this week? So many systems are combinations of 2 or more subsystems. Hybrid systems are very common in our day-to-day lives. In this assignment, students, that's you guys, will develop a mathematical model for the equations of motion for a rotational electromechanical system, but not just any rotational mechanical electrical system. This one right here. Please hold. I will show it. I will move my camera and everyone at home will get sick. Please hold. Be nice and I'll stop the video. What I get? Okay. You can do it, everybody. Promise. Oh, that might work. Let's find out. No? Hey, there's a thing on the table. Awesome. Great. This is our system. Right? There's video of it operating on YouTube, right? Dr. D and Professor Clark D Lab, episode 2. It's got some sweet music. If you guys haven't watched the video yet, I highly recommend. What's motor from the back end side. Now, in the video, it's for a power supply, provides the current, then drives here, right? Here causes this part to drive the force, which in turn also causes all three of these parts to be, right? Connected parts. If we're otherwise known as a shock absorber, right? These are RC called shock absorbers, so we get different mass to the part. So we estimated is around 200 grams.
Dr. D, we can't hear you.
What's up?
We can't really hear what you're saying.
Sorry. So the system has a motor that causes the gear to spin. The gear then drives all three of the carts. All right. So what your job is to do is to create the mathematical model for this, right, by hand, throw it into Simulink, and then see what your output looks like. What are you tracking? You want to track the motion of this cart, right? The very farthest one from the gear. Let's call it car 3. Seems like a good one to call it. You're given everything that you need, right? I've given you the parameters for it. I've given you B, K, and M for everything. I've given you the motor constants. I don't think that you should need anything else. If I were you, you can probably not see it very well. For those of you who are in the classroom, you see those white little carriages, those bearings that are on the rail there. You can assume that we have zero friction. They move pretty smoothly. I believe they're PTFE bearings on the rail. I forget. It's been a while since I've looked at this stuff. So what are we supposed to do, right? We make a mathematical model. You tell me what the output is on Simulink. Then you check your output to what you found by watching the video, right? And you compare how good your model is to what actually happened. And if it's not very good, explain why it's not very good. And if it is very good, explain why it is very good, right? That's pretty much the long and short of it, right? So you can work in groups, 2 to 3. Only one person needs to submit a report. That's fine. Right, it says here that it will be given to each group. We didn't make enough of those anymore. But you know, if in a perfect world, right, you guys would have run this in class and turned it on and done all the stuff. That is a loud lab. I'll tell you what, if you guys watch the video, it is as loud as you think it is. It's a day of, if I had to be in here for 5 hours of you guys running this thing, my head would explode. So thank God for small blessings, I guess. It's not as, I don't want you guys to get so bogged down like last time with trying to get minute data points and changes in the pendulum, right? Look at how it's displacing, just get an average of how the final mass is displacing, right? Just get an average of it, okay? You don't have to get crazy and get down and start using, dot and the dot and comma to go frame by frame to figure it out, right? Just on a gross scale, where are we, right? Yeah, and then compare the steady state response of your model to the model to the actual experimental condition, right? Typically, we use like, I would recommend using percent difference, right? Percent difference in your model, right? Assume that the experiment is correct and that your model is being compared to the experiment. That's how I would do it. As usual, it's very important to consider sources of error, right? So if you tell me human error, be prepared to lose lots of points, okay? Because human error is the only type of error. To err is human, but forgive divine, right? That's how the saying goes. I know I said it, I went there. So really think about it. Why is it not behaving the way that you think it should? Okay. Be very conscious of your units. Okay. Be very conscious of your units when you're doing things. There's one mouse. There it is. here are the parameters, right? These are the same ones that I gave you. You have to get KB or KT from the motor curve. It's on LoudCloud. When you open up the motor curve, you're going to notice that it's a really linear curve, right? So how do we find our motor constant from this, right? It's torque versus speed, right? That doesn't sound like our motor torque, right? Or a motor constant, but what it is. So how do you figure that out based off of this curve, right? You wanted a relationship between the two, right? Remember our motor torque equation is Tm is equal to KTI, right? Remember that? So I'll leave it there. The moment of inertia for the disc, right? So for the gear, modeled as a disc, 1/2 mr squared, or m is 1.1 ounces. I didn't give you what r was, right? I didn't give you what r was. I can give you r. I can give you r. I'll post what r is in my call. I forgot to forget. Okay.
So quick question.
Mm-hmm.
From the values that you're giving us, it's kind of making me think we'll have to do like a free body diagram for the gear and of course the masses, but I don't think there's an electrical diagram in this setup, right? Just because we don't have like your circuit or your voltage.
Good question, Trevor.
Or did you just do like 12 volts straight to the motor?
Good question. So I gave you what the current was.
Right.
But I don't know what the inductance of this motor is.
Hmm.
And I don't know what the circuit looks like. And McMaster Car is great and will give me all the CAD in the world, but they just won't tell me how it's made. So let me answer your question with another question. Is it essential for you to model the mechanical motion of this if you know what the output of the motor is?
Oh, so you don't. So no electrical circuit that I'm taking it.
Torque and current. Do you need to know everything else that's going on under the hood, or is it just enough to know what K is?
I think K is fine then. Okay.
Yeah, it's a good question, right? Because you could waste a lot of time making a electrical model for this, which we don't specifically need, nor do we know what the specifics of it are, right? Okay, so I'll get you guys that radius. I have it somewhere in my office. I'll post it later today. Okay. I would highly recommend starting the lab yesterday if I were you guys. Definitely don't wait till Sunday. That seems like foolishness. Right. I would at least take a look at it tonight. Start trying to get your equations ready. There's multiple ways that you guys can do this, as you know, right? You can use transfer functions or you can use state space, one or the other. You could use integrator block if you want, right? You guys. So, keep that in mind, right? Just figure out how you want to do it and start working on your equations. You can always come to office hours to discuss this with me. I'll talk to you guys about the mathematical model part of it, but remember, I'm not going to grade lab reports before I grade lab reports, right? So I'm not going to like proofread your lab report and then give it back. So I will talk all day about this, right? And the Simulink models and everything, right? But yeah, that's where I draw the line. No office hours today. Unfortunately, I have a meeting that runs from 3 to 5. I would much rather spend the time in office hours, but that's not my fate today. My fate is to sit in a boring 2-hour meeting. So that's great success. Right. All right. You guys have any other questions on the lab?
I mean, just real quick, is the motor curve just going to basically be a ramp input in Simulink?
So, Trevor, you don't need to use the motor curve in Simulink at all. You can use the motor curve to get K. And then you can decide. I'm leaving it up to you guys to decide what the best type of torque input you think is happening on this system. Okay. So once you know the torque, right? Well, let's back that up. You can input the current into your block that transforms it to, right? It's just a game that changes your current into your torque, right? So what's your input current going to be, right? Think about that. You're told what the value is, but well, how do you model it? So I want you guys to think about that. Okay. All right. Any other questions?
Your camera disconnected again. I don't know if you know. There we
Does that
go.
change? Do you have questions now?
I'm good. Thank you.
All right. All right. Cool. I'll get you that release. Here's the results thus far. Life livers, Dr. D, sanitizers, Zoom engineers, uncalibrated calipers in the bag. Yikes. Static waffles, SDCTA, Michael Scott Paper Company, 185.31, Doctors Without Doctors, War Zones, The Swarm Lord, Zero Division, Matilda's Pointing Compass, Wizard Lizard. Okay. So, still pretty close. Here's the thing. We're going to start on, not this week, but probably next week, a different kind of activity, right? Where you're going to be able to, in addition to the weekly activities, you'll be able to wager some of your points, right? It's essentially it's Final Jeopardy. Right? I'll put a category up. You guys, as a team, will decide how many points you want to wager based on the category. Then I will ask you a question. You will talk about it for a few minutes amongst yourselves, and then one person from each group will give me their answer, and you'll either gain the points or lose the points accordingly. I tried to do this with Family Feud last year, but apparently not enough people have watched Family Feud, and I needed to explain the rules way too often. So Jeopardy, everybody knows Jeopardy. We'll just go with that. All right. But that won't be this week. That will probably be next week, just so you guys know. All right. So we're going to continue with Laplace transforms, right? So when we left last week, and I know you probably can't read this at home, and that's fine. I'll put it back up on the screen in a second. When we left last week, we had done a problem, right? We talked about what is the definition of a Laplace transform, right? And the definition, by definition, of a Laplace transform, if we're taking a Laplace transform of a function of time, it is the same as taking the integral of that function between 0 and infinity when we multiply it by e to the negative st. Right, so let me write that down right here. Right, so if I want to take the Laplace transform of a function of time, this is equal to the integral from 0 to infinity of f of t e to the negative st dt. All right, I'm going to give you guys 15 minutes to do this one. You guys do it. Based off of the definition that is written up there, should be everything you need to do this. Mhm. Anybody have any questions? Yeah. Any questions? Everybody doing all right? I'm gonna invest in a 3D camera by the end of the semester, guys. Promise. Then I can do cool stuff like, oh.
They should have done a 360 camera and given everybody Oculus Rifts and let us be there virtually.
Seems cost effective, Trevor, for sure. I agree. That would be awesome. Maybe you could all be like holograms, like sitting at home. Right? And I would be like a hologram in your house, right? Walking around. Sweet. Just like the Emperor. Missed opportunity. All right. Does anybody else want the extra time? Is everybody feeling pretty good? Yeah. Everybody here good? Yeah. 15 minutes is too long. Okay. Everybody's done. Everybody's got an answer. Yeah. All right, so let's start here. Everybody's got an answer. What is the answer? Let's try that.
Negative A over S.
Negative A over S. Okay. I've also got a positive A over S. This is going to be a battle. Fight to the death. You guys sign the lab waivers. It's fine.
Positive.
All right, so let's take class vote. Who thinks it's positive A over S? Look at, if you think at home, if you think it's A over S, put a 1 in the chat. And do that. Who thinks it's negative A over S? Who doesn't want to answer? So they're just going to wait until I give the answer. That's going to be option 3 in the chat. Okay. So yeah, it is. It's positive A over S. Great success, everybody. Okay. We can calculus with the best of them, right? Got a lot of ones. Looking good. Looking good. All right. Solid. All right. So yeah, right. Say over S. So look back to the also, right? Also, you could look back to the example that we did in class on Thursday, right? Where we had A times E to the negative AT, right? And if A was 0, this would be the same problem. And so if that was A over S plus A, then you end up with A over S. Right? Could you have used the Laplace transform tables for this? Sure, but that's not the point. Okay, that's not the point. We're going to have plenty of time to use the Laplace transform table. The point was to do it once by hand so that we know. Now that we've done it by hand, right, using the table will feel so much better, right, because we put in the hard work of doing this, right? And I know that that was something you were all concerned about, right, is not feeling like you earned the Laplace transform tables. I know that this morning you woke up and it was a big concern, but you've earned it now, guys. You've earned it. How do we do these things, right? All right, so there we go. A over S. Anybody have any questions on this? What is this, right? What is this physically? What does this represent? If I had A over S, what would this be? Do we know? Do we have any idea? All right, so think about it, right? I have some function in the time domain that is a constant. What is that? What does that represent to us? One more time. I mean, not a line. the other, it needs more context, right? So in the context of, say, an input to a system, what would a constant be? So think about it, like if I give you a constant torque, and I said this is the input to my system, what kind of input would that be? Right? We've got different flavors of inputs, right? We've got ramp, ramp and hold, full step. What is it? If I'm giving you a constant, what kind of input is it? It's a step, right? A over S is what the step function looks like in the Laplace domain, right? Where A is the strength. So 1 over S is the unit step. And if you look at your Laplace transform tables, right, it will say like step input, right, on there. Because the thing about Laplace transforms is once you do them once, they never change. Right? This will never change. This will always be A over S, which is why the tables were made in the first place. Okay. So step function. That's important, right? We're gonna use the crap out of that. It's a technical term. Let's look at a Laplace transform table. Speaking of them, right? So in similar fashion, we can compute Laplace transforms for basically any function, right? With just the varying degrees of whether or not we remember how to do integrals on certain functions, right? So for unit impulse or the Dirac delta function, we get 1, right? So when unit impulse is just 1, what if I had an impulse of 10,000? It'd just be 10,000, right? Unit step or capital U of t is 1 over s. A is A over S, right? Which is, checks out with what we just found. Unit ramp or T is 1 over S squared, right? And so on and so forth, right? You'll notice that this one is circled, number 6 here is circled, right? That's the one that we used in the first example or the last example we did in class last Thursday. 1 over S plus N. Okay. Right. There are some of these that are very common. There are some of them that are not. Right? If you Google Laplace transform tables, you'll find some tables that are extensive. But we're never going to see some of those, right? The one that I've provided you in the announcements last week, some of you will likely notice that it is blank, right? But that has the ones that are most common for this class. That has the ones that are most common for this class. We'll talk more about that in a minute. Oh, so you want to use MATLAB to get the Laplace transform? Okay. Well, we can do that, but you need the symbolic toolbox, right? So you type sims t, that defines t as our symbolic variable. We'll create the function f, lowercase f being the time variable, or the time domain function, capital F being a Laplace domain function, right? Lowercase f is equal to 3 sine of 2t. And capital F, we use the command Laplace, all lowercase, Laplace of f, that returns the Laplace transform. And then we're going to use probably the most important MATLAB function that you will learn all day, which is pretty, which gives you the typeset mathematics for your Laplace transform. I'm not even kidding, that is true. It's a true thing that's in there. All it does is makes it look nice like that. Debatably, I don't know that that personally looks nice to me, but you know, you can use it if you want. Doesn't matter. Doesn't affect your result, just affects the output. Right. So we get 6 over s squared plus 4. Right, and we started with 3 times sine of 2t. Let's go back to our table and check, right? So 3 sine of 2t, well, we got a sine, right? Mine was specifically 3 sine 2, right? So I should have something that looks like this, or this is omega, so this should be 2 over s squared plus 4, but I had a constant, so I should multiply by 3, all right? Because remember, we didn't go over properties yet, but spoiler alert, right? We saw it with the integral we just did, you can pull the constant out, right? So 6s squared plus 4, right? 6s squared plus 4. Apparently my camera has decided to go offline now. It's fine. We're good. So we should get 6s squared plus 4, and in fact, we got 6s squared plus 4. Great success. The tables work, right? Okay. So we can have MATLAB to do it using the Laplace command as long as we use the symbolic toolbox. All right, and that's nice because that'll help us check some of the things on the homework that we need to do. Any questions on the MATLAB stuff or the Laplace transform table stuff so far? We doing all right? Well, maybe. Okay. Okay. So what about poles and zeros, right? We heard a little bit about poles in the video that we watched at the beginning of class. All right, so let's say I have some Laplace transform for a function, f of s here, right? And we can make it look like in this form, where if I've got my numerator, it'd be some constant times a series of factored coefficients, right? So s plus z1 times s plus z2, all the way out to s plus zm. Then we can have our denominator, right? And this would be a factored denominator as well, right? Remember the denominator of our transfer function is the characteristic equation. Is this the characteristic equation? Not necessarily, right? Because we'll talk about why in a second. Right? So what are the zeros of my function? The zeros of my function are the values for s that cause the numerator to equal 0. Right? So imagine we just had everything over some constant, right? Any one of the values, negative z1, negative z2, all the way out to negative zm for s would cause the whole thing to zero out, right? And that's what a zero does. Zeroes out our function. So poles, on the other hand, which we know are typically the roots, the characteristic roots of our system. These are the values that make my function infinity, right? Because 1 divided by 0 is not 0, as some people who don't work here anymore try to tell you. So it's not. But, like, all right, so let's think about division by 0 for a second, right? What is that actually telling you? It has to be infinite, right? Because I can divide anything into an infinite amount of groups of 0, right? When you divide something, you're just grouping it into groups of whatever the number is, right? Well, I can divide anything into an infinite group of 0, right? It doesn't matter. So what is the reason for wanting poles, right? Well, went over it in the video, right? The poles tell us something about the dynamics of the system, right? The poles are going to tell us what frequency we spike at, right? So for this simple example here, right, f1 of s is equal to 1 over s plus 3. I have no zeros, right, because I have a constant on the top. I have a constant in the numerator. And I have one pole at s equal to negative 3, which determines what kind of function I have, right? Because that's going to tell me, right, if I take this f of s and I bring it back into my Laplace transform table, right, so I have 1 over s plus 3. I bring up here, hey, look, 1 over s plus a, 1 over s plus 3. That means I should have e to the negative 3t. Right? Okay, great. I've got e to the negative 3t. That's not going to erase there. Yeah, got it. E to the negative 3t, right? Which is what they said. Let me ask you a question about e to the negative 3t. What's the time constant of this response? You have e to the negative 3t. What's the time constant? It is 1/3. Excellent. Right? The tau is 1/3. How do we know that? Well, remember, tau is the amount of time that we need to get e to the minus 1. right? Which in this case is wonder, is it seconds, days, months, hours, years, millennia? I don't know, right? Literally all I was given is this Laplace transform. I have no idea what this system is or what it does. I'm going to assume seconds because that seems reasonable. Third of a day, tau would be pretty excessive. 8 hours. Last time I checked. All right. Cool. Is it stable or unstable? Why? It is. It's stable because the exponential is negative, right? So it's an exponential decay. So as time goes to infinity, the response dies out. All right. Do you guys have any questions on Laplace transforms in general before we jump into properties and theorems, right? So this is all great so far, right? We can get a Laplace transform, but we need to know how we can manipulate Laplace transforms, which is the next part. And then we'll talk about inverse Laplace transforms after. Okay. You guys have any questions? No? All right. Laplace transform properties, right? And a couple of these you've actually seen in action, right? Because based off of the definition. But the thing to remember about Laplace transforms, the thing that's important to remember about Laplace transforms is they are linear operators. Okay, so linear operators. And so because of that, we can use our superposition properties, right? So this first one, property A here under superposition, is saying that if you take the Laplace transform of some constant times a function of time, it is equivalent to the constant times the Laplace transform of the function. Right? So in essence, you can pull the constant out, right? And we showed that in the last one that we did. When we take the integral, you pull it out of the integral, right? It's not affected. It's not affected by the definition of the Laplace transform, the constant. The second one, right? The second one says, if I have the Laplace transform of two functions that are being added, this is the same as A1 times the Laplace transform of the first plus A2 times the Laplace transform of the second. Another way of thinking about this, right, is that Laplace transforms can be distributed. The way that a mathematician would tell you is that if you take the Laplace transform of the big thing, it's the same as the sum of the Laplace transforms of the little things. That's exact word for word from a math textbook, 100%. Right. But it's distributed, right? You can distribute the Laplace transform, which is nice because we're going to see that we actually use this one quite a bit, right? So I'm going to put a red box around this, because this is an important property that actually is going to get used a lot by us in this class. So those are my two linearity properties. We can also define properties for differentiation. The guy talked about these in the video at the beginning of class a little bit. And we don't always assume that the initial conditions are zero. And in fact, that's not appropriate to always assume that they're zero because they can be non-zero. There is a very specific case, right? The transfer function, when we have zero initial conditions, we'll talk more about that, right? But for right now, let's just write it in the general way, right? So if I take the Laplace transform of the derivative of a function of time, this is equal to S times the Laplace transform of my function minus the initial condition, f of 0, f naught. I'm going to say something now. I'm going to say something now, and I realize how ridiculous it's going to sound, but just bear with me. The Laplace transform of a function is the Laplace transform of the function. The Laplace transform of f of t is f of s, right? We don't know. So if we don't know what the function actually is, you can write it as f of s, x of s, g of s, whatever of s, right? And this is helpful for us, not specifically right now, but when we're going to talk about inverse Laplace transforms in a little bit. So that's the first derivative. What if I have a second order derivative, right? F double dot. Well, it's s squared times f of s minus s times f naught minus f dot naught, right? So we can extend this as many times as we want, right? And in the general case, if I have the nth order derivative, and if I have the nth order derivative of a function that I'm taking the Laplace transform of, this will be s to the n times the Laplace transform minus s to the n minus 1 times the initial conditions all the way down until we get our function, or all the way down until we get to the n minus 1 derivative times the initial condition of the nth minus 1 derivative. Okay. For this class, really, if I'm going to be honest with you guys, right, these are the two that you really want to, like, these three properties are going to show up a lot. They're going to show up a lot. If you look at the master sheets, right, you're given the general form of this, right? Let's test the general form, right? I wanted d squared over dt squared, right? Second derivative. Well, I get s squared f of s minus s times f naught minus f dot naught, right? The general form works, just plug in whatever order that you have and crank it out. You guys have any questions so far? We're doing all right. Just writing down properties. Yeah, come. So good question, right? The question was, when we get to part, like the fifth step of our modeling process, the analysis portion, right? Are we going to be using this? The answer is yeah. We'll get there. Right? I'm going to introduce the properties first, and then we'll talk about how we're going to use these to get a time domain response out. Okay. Good question. Okay. Any other questions? We've got a couple more properties. You can take the Laplace transform of something that's being integrated, right? So Laplace transform of a function integrated from 0 to some time t is equal to the Laplace transform of the function over s, right? Or 1 times, right? So we can also write this as 1 over s times f of s, right? And I want you guys to see this, because as it turns out, if you want to integrate something in the Laplace domain, you multiply by 1 over s. And if you wanted to take the derivative, you would multiply by s. Right? I'm going to go back for a sec. Look at this first derivative, right? The derivative of my function is s times the Laplace transform of my function, right? Minus the initial condition, right? Minus the initial. So s represents the derivative in Laplace space, and 1 over s represents an integration. Blake. Just so it's not t everywhere. Question was why they use tau, because using t everywhere gets confusing. It's from 0 to t. What about multiplication by e to the negative at? We're probably not going to see this one a whole lot in this class, but we can handle it, right? So isn't this just become what we were talking about a little bit with what we were talking about, what the video was talking about Fourier transform? A little bit like that. But essentially what happens, right, is if you have some function times e to the negative at, the Laplace transform is just f of s plus a. So instead of being f of s, you'll have f of s plus a. Why? Well, remember, you'll end up with this, right? Which will inevitably allow you to do that, right? To be able to consolidate those two exponentials in this way, and so instead of having s by itself, you'll have s plus a. Again, that one doesn't come up as much. Right? The ones in the red box from the previous slide, those are, you're going to see those quite a bit. You're going to see those quite a bit. Okay. Okay. So that's all the properties we need to define. What we're talking about next is some theorems, right? So there's some ways that we can, some theorems, some essentially laws. Right? Give me a sec, because I forgot that this had my stuff. I apologize. Excuse me. So we can talk about the final value here. Yeah, that'll be fine. That'll work. Okay. So what is the final value theorem, right? Well, the final value theorem is how we figure out f of infinity, right? Which is really, because we can't evaluate something at infinity, right? It's really the limit as time goes to infinity of f of t, which we can define in the Laplace domain as the limit as s goes to 0 of s times f of s. What happens as time goes to infinity? As time goes to infinity, if we have a stable system, we will reach steady state. Right? So essentially, we are trying to figure out what is the steady state response of our system. Right? Trying to figure out what's the steady state value of our system. The final value theorem only holds true when our function reaches steady state, or a constant value, a constant steady state value. So, right, for when time goes to infinity. So the final value theorem would not and does not exist for sinusoidal functions. So for things that oscillate harmonically, right, when we have harmonic oscillation, we cannot define a final value because there is no final value, right? It bounces around. Does that mean that there's no steady state? No, it just means that it doesn't reach a constant value steady state. So the first thing that we're going to have to do, right, is make sure that the final value actually does exist, right? Before we start going through a final value theorem test. And the way that we do that is we check the roots. Right? We're going to have to check the roots. So that's final value theorem. And notice, right, it's f of t, or it's s times f of s, right? S times f of s. We can also talk about the initial value theorem, right? So the initial value theorem is for finding f of 0 plus. What is 0 plus? 0 plus is that infinitesimal amount of time right after 0 seconds, like right after the split second, right? Whenever we do impact problems or in dynamics, we're gonna look at it right after contact with it, right? There's not enough time for this thing to fully develop, but it's the initial response of the system, right? So there's not enough time to reach steady state, obviously, but it's just enough time for it to be in contact that we'll start to develop some sort of response, right? That's what we're looking for, right? So the limit, this is the limit as time goes to 0 plus, or in the Laplace domain, the limit of s times f of s as s goes to infinity. As s goes to infinity. And by doing this in the Laplace space, we should be able, right, these two things are equivalent, and we'll be able to get what the initial value for a function is. All right, so that's all well and good, but how do we use these things and why do we use these things? Right? Yeah. We'll get into that in a second. You guys have any questions? Are there any cases when you don't use initial value theorem, like when it wouldn't apply? Is that the question? Yeah. So if you wanted to know the initial value of the system, right, then you use it. There's no, so it's not like final value where there might not be an initial value of the system. Right. There's no cases where initial value won't exist. All right. So I want you guys to take, I'll give you 10 minutes to do this. Find a Laplace transform. Feel free. I'm going to give you a couple seconds to write it down. Then I'm going to go back to the table because you should feel very free to use the tables here because, I mean, that looks like a lot of fun to do those integrals, but let's stand on the shoulders of giants for this one. And so take a couple seconds, write that down. I'll pull the table back up. So I want you guys to apply what you know about Laplace transform properties and using the Laplace transform table. Do this, right? I'll write the function. Here, remember it is f of t is equal to 0.2 plus 2 e to the negative 3t minus 5 e to the negative 6t plus 8 sine 4t. Right, there's the function. So, would this be something we could break up using linearity to make it easier? Yes. 100%. All right. You guys want any more time? It's being annoying. So, all right. You guys good? One more time. What's up? It's not like those are two questions that were diametrically opposed. So it's like saying yes is not super helpful. Um, Possible, maybe. Maybe. All right. Everybody at home, you good? You want some more time? I'm gonna guess that everybody's okay, because you're all looking at me on your cameras and not giving me any inclination that you're not okay. Blink once if you're okay. Okay. So what are we gonna do, right? What are we gonna do? Let me get rid of that. We'll go back over here. All right, so we had some properties. Okay, we're doing this. Now, you could totally, if you wanted to, right, take the Laplace transform of this by hand and use the definition, but I would highly recommend against that, right, because what we really want is like this, which is just the Laplace transform of 0.2 plus 2 e to the minus 3t minus 5 e to the minus 6t plus 8 sine of 4. Right, we want that. We want that. And obviously, that's an entry in the table that I just haven't shown you, because this is a very common function that everybody would use all the time, which it's not. But we have a Laplace transform property that makes this very easy for us to do, right? Because we can distribute the Laplace transform of each of the parts. So this becomes finding the Laplace transform of 0.2. Well, 0.2 is a constant, right? So the Laplace transform of f of t, if I do this by parts, well, Laplace transform of 0.2 is just going to be 0.2 over s, right? The Laplace transform of these two, right? These are both exponentials, right? So e to the negative 3t. Well, this is going to be 2 times e to the negative 3t. E to the negative 3t gives us s plus 3. We're going to subtract. Well, this is 5 times e to the negative 60. Again, e to the t is s plus a, right? In this case, a is 6. E to the negative t is s plus a. And then we've got 8. Well, let me use the last color here. Right? Then we've got 8 sine of 4t, right? So this is going to be 8 times, well, sine. Sine is omega over s squared plus omega squared. Omega is 4. Or, if you wanted to get crazy with it, right? 32 over 60. Sean. Right there.
All right, so when it says e to the like negative 18 and s plus a, do we not make that like minus a instead of negative a?
No, because remember what s plus a is, right? S plus a, think of it as being the characteristic equation or the root of the system, right? So e to the negative 3 is telling you that you would have a root of s plus a, because we solve for s. It's going to be negative 3. Right, yeah, yes. Yeah. When you're reading this, right, if you're reading this particular table, right here, you see that A is there. That A is the number, and that just goes directly in. Okay? Don't worry about the sign. Don't worry about the sign. Some tables give it more generally and don't tell you what the sign is. So just be aware. Pretty sure the one that I gave you was more like this.
And then the one that's 0.2 over s, I have it as just 0.2 staying constant. So why is it 0.2 over s?
Because this is a constant, right? We didn't have a unit impulse, right? We weren't told that was an impulse. We were told that it's just a constant. It's just a constant, right? Right. Exactly. Right. So, yeah, in the problems that you're going to see, right, it'll be kind of like, trying to think, last homework. I think that there So you know, how, like the last homework, I told you, hey, do this in Simulink to all these different types of inputs, right? It's gonna be like that, except that you're gonna be given, you're gonna be told like, do this to a step input, do this to a step of 50, do this to an impulse of 500, right? You're gonna be given one input, and then you're gonna have to run through the loop to get the output, right? We'll talk about what that loop is in a second. Good question. Any other questions? Any other questions? No? Time is it? I think we're doing pretty good on time right now. All right, so bottom line here, right? If you're asked to do something like this, use the tables. Use the tables. Why they're there, use your tools. In the real world, you know, if your boss ever needs you to take a Laplace transform for something, which nobody will ever just come into your office and say, hey, I need the Laplace transform of this on my desk by the end of the day. Okay, it's not, be honest with you guys, it's not something that's going to happen, right? But if it did, don't waste your time. Use the tables, right? Unless your boss is really specific, unless you're in like a really strange movie, like Die Hard-esque movie, where the only way to get out of the situation is you have to do the Laplace transform by definition, right? I would probably just use the table. All right, now that we've gone off the rails completely, let's talk about another example. Oh, before that, participation this week. You know that blank Laplace transform table that I posted in LoudCloud? Before next class, you guys need to fill it out and turn it in before class. Private message it to me. The question is asked, do we have to do it by hand? Meaning, do we have to write it in by hand or can we type it? You can certainly type it using Microsoft Equation Editor. That would be acceptable. But also make it easier because then you don't have to like scan it and upload it and do that, right? But yes, try those Laplace transforms. When you get your exam in a couple of weeks, right, you will have a Laplace transform table that you won't have to like worry about filling in or anything, right? But I want you guys to get familiar with the Laplace transforms and how they work and how they together. Right? So before the start of the next class, just shoot me a private message with the complete table. Yeah. It also has the added benefit of then you'll have a table that's actually applicable that's condensed for the things that we use in class, as opposed to having one that's extraneous and does everything under the sun. All right, so let's try this. Right? Given this Laplace transform, I can tell it's a Laplace transform because it's a capital letter that's a function of s, which is equal to 7 times the quantity s plus 3 over s squared plus 2s plus 10. I want to find the final value theorem, if it in fact exists, and the initial value theorem. So let's do this one together. Let's start. Final value theorem. First of all, does it exist? I need to find the roots of the characteristic equation. What are the roots of the characteristic equation? What are the roots of the characteristic? Say that again, Jake. No, that's going to be the 0, right? That's going to be the 0. And to be honest with you, in this class, we're not really going to talk about the significance of zeros at all. They contribute to phase and, well, so we'll talk about it a little bit in frequency domain, but for time domain stuff, they don't matter. That's not entirely true, but they don't matter for us. Here we go. I hear something say it's too hard. Fun. Man, that's good. Oh, that broke my heart. If that in fact is true, that I did that. I hope it is. All right. What are the roots? It's important, guys. We need to know the roots, right? Because why? If we know the roots, then we understand what the response is supposed to look like. Okay. Also, then you don't have to waste your time doing final value theorem if you don't have to do final value theorem. And there are questions on the homework that are going to force you to do final value theorem and test whether or not it exists. So quadratic formula, solve the bottom equal to 0, one of the two. What do we got? Spoiler alert, the follow-up question is going to be, what does it mean when you find out what those roots are? Spoiler. The roots, not the band, but the roots of the equation. All right, Sean, what did you get? All right, you got negative 0.1 plus or minus 0.3. Yeah, you're off by a factor of 10. You're off by an order of magnitude. It should be negative 1 plus or minus 3j. So follow-up question, what does that mean? What does that mean? If I've got complex conjugate roots, what does that mean?
Does it converge because the real part is negative? Or am I?
No, the real part being negative is good for us, right? Because that's going to be a left half plane root.
Right.
So give us stability.
Stability, thank you.
Stability and convergence are two different things, right? The video, don't confuse the guy talking about convergence in the video with what we consider to be stability. Okay. Think of convergence as the two poles are going to move. You saw how they moved with time. They're going to eventually come together. That's what they're talking about as convergence. All right. So what kind of response would you expect from a complex conjugate? You've got, yeah, Chris. Stable, all right, one. That's one part of it. So how would you describe what it's going to look like? Like if you had to plot it, what would it look like? Sinusoidal and, yeah, you guys got one together. Your table got it together, right? It's sine. So show you guys what Chris said would be like that, which is true. It would be an exponential decay, but it would also be, you know, this thing. Right? That's a horrible illustration. It's a sinusoidal decay, right? So we would expect some sine wave that decays over time. Okay, great. So because we know it's going to decay over time, we're expecting this to reach a final value, right? Because eventually we'll get the transient portion will go away eventually. Okay, great. So because of that, we can run through our final value theorem, right? So we want f of infinity, which is the limit as s goes to 0 of s times f of s, right? Which I will rewrite as the limit as s goes to 0 of 7 times s plus 3 times s over s squared plus 2s plus 10. And if I take the limit as s goes to 0 here, what do I get? So at steady state, my transient response decays to 0, and we're good. So we get a final value of 0. Perfect. That's what we want. Now, all right. So is everybody cool with limits? Everybody's cool with limits on this one? All right, the long and short, right? Plug in 0 for s and see what happens. Hopefully you don't get 0 over 0, right? Because then the world erupts in fire and all that. Yeah. Fine. You need to find the roots to make sure that you're not wasting your time doing the final value theorem to begin with. Because if you have something that's a harmonic oscillator or unstable, it's not going to have a final value. What about the initial value? F of 0 plus, which is the limit as s goes to infinity of s times f of s, right? And so I'll rewrite this time by multiplying it all out, right? So this is going to be 7s squared plus 21s over s squared plus 2s plus 10. All right. So I take the limit as this goes to infinity, and I get this, which is obviously 1, right? So we're good. We're good. Oh, no. What do we do? Well, we panic, right? We go through the 5 stages of grief, right? The denial, anger, all those things. And then finally, when we get to acceptance, right, we realize that we've been training for this, right? We get it. We channel all of our famous French mathematicians from Calc 1 and we apply L'Hopital's rule. to this, right? And to paraphrase, L'Hopital's rule basically says that the limit as something approaches infinity of the function is the same as the limit of the numerator of the function, the derivative of the numerator divided by the derivative of the denominator. So we're going to take the derivative of the top and the derivative of the bottom, and we're going to test the limit again. Okay? So, L'Hopital's rule, right? So we'll take the limit as s approaches infinity of 14 plus 21 over 2s plus 2. Well, once again, we see the problem arise, right? Well, we got to do it again. Was it? I forgot an S. Fine. Don't worry. Don't worry about that. It was there the whole time. I know what you guys are talking about. So hey, check this out. Right? If I take, you know, why don't I write it? Could write the whole thing out. Right? Why don't I do that? Limit as s goes to infinity of 14 over 2. Great success. Also, I meant to do, that's an important part of the process. When you recognize you have to be sad. Okay, so hey, we got 7. Fantastic. So you haven't seen him in a while, but your old friend L'Hopital coming to the rescue, right? He ran out of gas on the 202 and he's there. That was good. Wait. I don't know, you tell me. I never took calculus. I went to school so long ago, they were still inventing calculus, guys. So yeah, I mean, if you look at what's going on, right? Eventually, you're just going to end up, as long as you have the same order, that would play, right? But the issue comes up with applying a rule like that if the bottom was s to the third and the top was s squared, right? So yeah, fine. It's a great question. How often do you use L'Hopital's rule? It's pretty much all the time with initial value theorem, because you end up getting infinity over infinity quite a bit. And you can tell right off the bat, right? You're going to have to do it twice, right? Because you got to get rid of the square. Take the derivative of the top and the derivative of the bottom, and then evaluate the limit. Right, so where it comes from is if you have a function divided by a function, right? So if you have a single function, f of x, that is equal to g of x over h of x, right? And you take the limit of that function as x approaches infinity. If it is infinity over infinity, it turns out that by taking the derivative of g of x over the derivative of h of x, this is equivalent in terms of the limit. The limit of the derivative of the numerator and denominator function is equivalent to the original limit. And that extends for many derivatives as we take. Okay. I'll post a video with the formal L'Hopital's rule thing in Discord for everybody to scope. To peep, as the kids say. To peep that L'Hopital's rule video. Oh man, he said that. That's all. All right. All right, let's do this one. All right, so what you see this, the first thing you do is you think to yourself, I'm very excited because it's my opportunity to find the roots. So find the roots. Find the roots, tell me what they mean. We're running out of time. Oh. This one should be a little bit quicker to get the roots of because it's already factored for us, right? So what are we looking at roots wise? -4, sure. Plus or minus 5. 0. Plus or minus 5 what? J. Right? Because it's square root of -5, right? If s squared plus 25 equals 0, so it's s squared is equal to -25. Square root of -25 would be -1. Square root of -1 times 5. All right. There it is. Yes. So what does this mean for us, right? What does this mean for us? This is a little tricky because you're going to say, well, we've got -4, so it's stable. So it obviously is going to reach steady state, right? Because it will decay e to the -4. And you're not wrong, but you're also not right. Because remember, the last one, e to the 3t was tied directly to the sine wave, right? They were one function together. This time, each part is separate. So we have a marginally stable system at 0, right, which has no real part and no imaginary part. We've got a purely real part at -4, which is going to cause an exponential. But we've got this harmonic oscillator at plus or minus 5j that is going to be oscillating continuously at 5j, right, at 5 times t, 5 radians per second. So in this case, yes, that exponential goes away, but the oscillation never fades. So there is no final value to it. It does not exist. That is not to say that there is no steady state, and we'll talk about what that means when we get the frequency response, but there is no final value. There's no one value that this hits that we're asymptotic towards, right? So all we need to do is run through this, right? Run through the initial value theorem, which we know already by looking at this is going to be super fun, right? We can all tell. I know. Based on the last one, right? So s times this gives me 3s times s cubed plus s squared plus 6s plus 12 over s times s plus 4 times s squared plus 25. Well, look at that. Those s's ought to already cancel, right? We're going to get rid of something. But as you can tell, we'll end up with infinity over infinity, right? We end up with infinity over infinity. So we're going to have to do L'Hopital's rule. And how many times are we going to have to do it? 3 times, because we've got s cubed on top and s cubed on the bottom. L'Hopital's rule. I'm not going to write the limit every time. Just remember that we are taking the limit, right? Still infinity over infinity. Sorry. Still infinity over infinity. Remember, in each of these cases, I am taking the limits of these functions, right? Taking the limit of these functions. Oops, almost fell down. This chair has wheels, guys. This chair has wheels. Okay. So we have any questions on this? I still haven't really told you guys why we want to do any of this, right? Yeah, sure. Why do the roots mean we have no final value, right? Here's the real imaginary axis. That's supposed to be on the axis. There's -4, 0, and then something here, right? This response by itself is e to the -4t, right? So what this is telling us is that there are, in fact, 4 separate responses, right? This being on the axis is still going to be mostly oscillatory because there's 0 real part, but so and this here, these two, that's a harmonic oscillator, right? So, and they're a complex conjugate pair. So if we were to write this out, right, you would get what? You would get, well, you would e to the -4t plus e to the 0, right, because of the 0 there, plus, well, this is just sine of omega t. And so as time goes to infinity, we're left with a shifted sine wave. So, we're left with a shifted sine wave. I think we have just enough time to start talking about inverse Laplace transforms, and we'll get into it next class, right? But I want to introduce them. Do you guys have any other questions? Yeah, go. See, what's that? 3 is the initial, this is F0, right? So yeah, 3 is F of 0 plus, right? On the homework, there are definitely problems that are going to have to do final value and initial value theorem for various Laplace transforms that you're given. Okay, so you get some
Professor?
What's up?
For both of the examples we just did,
Mhm.
the initial volume ended up being the first coefficient. Will it always be like that, or is that just coincidence?
Not necessarily, but it turns out to be like that because both the top and the bottom were of the same order. If they're not of the same order, then you can't make that generalization.
But if they are of the same order, then can we just jump straight to it?
Typically, it will just be the same. I'll post this video in LabClub. Okay, so great. We can take a Laplace transform and understand the properties of Laplace transforms, right? But I still haven't proven why this is a useful thing that we want to know, right? Why do we care? So I want you to think about that. I don't know if you guys are big X-Men fans or not, but I'm going to use an analogy from the X-Men, right? Nightcrawler, the mutant who can teleport. The way that his teleportation powers work is that he goes into a different dimension, then he pops out someplace else, right? Okay. Right now, So his powers would really suck if he couldn't get back out, right? He'd just be stuck there. Right now, we know how to get things into that other dimension, but we don't know how to pull them out, right? We know how to make something go into the real complex plane, right? The real and imaginary plane, but we have no idea of what that means or how to make it into something useful for us. That is going to change with the inverse Laplace transform. The inverse Laplace transform allows us to take the Laplace transform of a system, right, of our modeled system, bring it into the Laplace domain, rearrange it using algebra, and then pull it out using the inverse Laplace transform. What is the inverse Laplace transform, right? Because we came up with a definition for how to get the Laplace transform. But is there an inverse Laplace transform definition? And the answer is no. So how do we do it? A systematic approach for solving ODE, obtaining the dynamic response. We take the Laplace transform for every term in our ODE. We incorporate the initial conditions using our differentiation properties. Using the results from that step, we solve the Laplace transform to the dynamic variable, which is typically y of s, or whatever else we're using. Then we obtain the dynamic response to the inverse Laplace transform, right? So where does this come from? So when we do these things, when we do this, which we'll start an example next class, we don't have time today. When we do this, okay, we're going to start off with a modeled equation, or we're going to model a system. Then we're going to take the Laplace transform of our equation and the Laplace transform of our input. We're going to use algebra. We're going to rearrange all the things, right, and solve it for our dynamic variable. Then you'll have y of s is equal to a bunch of stuff. We are going to look at that stuff, and we are going to try to associate it most closely with what is happening on page 4. I'll get there. What is happening in the Laplace transform table. Right? Because let me ask you this. If you saw that you had 1 over s plus a, 1 over s plus 3, as what comes out on the right-hand side, what's the inverse Laplace transform of that? Well, according to the table, it had to have been e to the minus 3t in order to become 1 over s plus 3. So the name of the game is trying to match closely. Now, when I say that, I mean exactly. If it doesn't match exactly on the Laplace transform table, you cannot claim it as an inverse Laplace transform. But there are some tricks that we can do. And what's going to happen is next class, we are going to have to use I told you guys this last time, one of my top 5 favorite expansions of all time, the partial fraction expansion. So we're going to have to use partial fractions to figure out what's going on. Okay? I'll leave it there because there's not enough time to go into the example, right? I honestly, I think this is, so for the cost of doing some algebra, you get the answer to a differential equation. Okay? It's a powerful tool, especially when we have very high order systems to be able to do this stuff. And it also leads directly in to not only transfer functions, but also impedance in circuits, which simplifies circuit analysis immensely. I'll put up the thing. No, thank you. There you go.